Good day to you on the 5th day of June. We are studying geometry, and over here you'll see some curves. This series will be a continuation of our series on continuity. You're basically looking at continuity when you're looking at curves. They're not straight lines, they're curved. The concept of continuity is strictly to do with curvature, but really it's that red one. Let me just expand. That represents a family of ellipses. We're going to be talking about this. You'll see that there is a number associated with each one of these lines, two of which are open. That's the family of hyperbole. The green is the parabola, which is a single item, and the red is a closed line. You know that the most compact form of an ellipse is a circle. A circle is basically the geometric definition of continuity. The circle is continuous because you can't get 2 points for a Euclidean line. First of all, there's no straightness, but also there are no points. Now, we will show that it is possible to discretize the circumference of the circle, which technically is called the surface. Really, the interior is not the circle. That's not what is meant when we are talking about a family of curves. It is only the line itself. Now, line has two definitions. It's quite confusing, but we can disambiguate that right away. The correct use of the word line is for anything you see on this diagram, including at the bottom a straight line. And that's how you distinguish between the two. The curves are lines because you can draw them on the plane. But the straight line is a special case of a line. And you can see that from this diagram. The straight line is extremely peculiar because it has no curvature. Everything in the universe has curvature. There's no such thing as a straight line, although we, with our physiology, can imagine a straight line. Now, you may object. You may say, oh my goodness, how naive of you, Scott. You know that we take a straight line distance to a star, and that's a straight line. That's true, and it's imaginary. It doesn't actually exist because it's incomplete. Did you know that? If you didn't know that, it's because you don't know anything about relativity. You don't understand space-time. You have no idea what Albert Einstein discovered. What Albert Einstein discovered is that it is impossible to take a straight line distance to anything. There's no such thing as a straight line. My goodness! Are we just making riddles here? No, this baffled an entire generation. And Einstein's discovery of what is called general relativity was not acceptable at first. As any great discovery, it simply had to be a work of the devil. It was just absolutely from hell. That's what was said about the number 0, and in fact about the negative numbers. And really, you can probably make a long list if you like to study science and history. You'll find out that new discoveries are rejected. There are very good reasons for that, although they turn out to be not very good reasons when it turns out the discovery is true. Now, the straight line is the most unusual object, and so why do I say that you cannot take a straight line distance to a star? You're believing what the photon tells you. Well, the photon doesn't know what happens behind it when it's traveling. Yes, that's what Einstein discovered. He didn't discover that photons take time to travel. That was known for centuries before Einstein. It was known that there is a constant speed. It is considered to be a constant speed called c, just a little letter c, which means a ratio of distance to time. So when you take a straight line distance, that's a distance. And that's actually redundant. When you take a distance, it is a straight line. That is called Euclidean. That is the only correct definition of Euclidean geometry. is that the shortest distance between 2 points, stop right there. You have to have 2 points. And now complete the statement. The shortest distance between 2 points is a straight line. Those are Euclidean points. And you know the definition of a Euclidean point? It has to be on a straight line. There's no other definition of a point. When you have a point, it is on a straight line, or it's not a point. So the straight line is extremely peculiar, and it's totally imaginary. Not totally. There's something called superposition. And it's the superposition between Euclidean geometry. When you take that straight line distance, basically the photon is telling you where it came from. But the problem is that it takes time for the photon to reach you. In the case of a star, it would be light years. So it traveled for at least 4 years if you're measuring to Alpha Centauri or Proxima Centauri, approximately 4 light years away. Well, it takes 4 years for the photon to travel. Of course, it's mini photons. But when it reaches your telescope, the photons dutifully report where they came from because you can see that star. That's where it is. No, it's not. No, it's not where it is. It's not where it is. I think you have to really exercise your brain if you've never heard that before. It just sounds wrong. That star is there. You can take a distance to it. No, no, no. What Einstein pointed out very carefully is that star moved. During the 4 years that the photon was traveling, the star is moving where it no longer is. And when you take that position, you're wrong. It's not there. What is true is that its relative position, relative to the rest of the sky, is virtually true. It seems like we have a crystal sphere of stars over our head, and you may know from your history lessons in science or your science lessons in history that it used to be thought of as a crystal sphere with the stars attached to it, which revolved. The same mistake was made in the notion that the sun is traveling at high speed every day, and it just really travels so fast every day. No, it's because the Earth is turning that makes it look like the sun is moving, correct? Well, this is exactly the same thing. Not exactly, but when you take a fix on a star, it's not there. It's moved. And that's called relativity. A very good question to ask, and you may be asking it, is what is this number here that's associated with each one of these curves? I'm just going to expand this a little so that you can see the numbers. Depending on the resolution of your screen, you see that the ellipse has E equals 1 over 2. The green line, which is a parabola, has the value 1. And the hyperbola has a value of 2. Those are common numbers, but the straight line has E equals infinity. What could that possibly mean? I'll be explaining that here, but I first want to let you know where this is from. This is actually taken from Wikipedia. But what does it refer to? It refers to some research done by Johannes Kepler, Isaac Newton, and Roger Bošković, to name the 3 most prominent men, who were investigating the evolution, called the evolute of one object into another. It's a continuous transformation using the notion of continuity. Now, you may not be able to see the very faint gray lines, but actually this is a continuous plane. Because it's made entirely of curvature, curves, and except for the straight line, which is considered in this system to perhaps also be a curve, but turned edgewise to us. So that you're actually seeing a circle, but you're looking at it lying flat. Now, the key term here is infinity. But what is that number? E stands for eccentricity. It is a mathematical property of these curves, which unites them on a metric. But it's not a linear metric. It does use linear numbers, but these are actually representations of numbers which are not linear numbers. They're in reduced form. Now, the 1 over 2 is not in reduced form. Every fraction is a two-component number, as you can tell just by looking at the number. 1 over 2 is not one linear number, it's two linear numbers. And we're taught in school, quite falsely, quite incorrectly, and actually quite propagandistically, that fractions are linear numbers. No, they are not. And I discovered that. It is a two-component number. Now, the reason why this could sound baffling, or it has sounded baffling to all the physicists and mathematicians who have ever lived, would certainly be baffled by what I just said. So if it baffles you, don't be surprised. I'm going to make this very simple so that you can understand what the difference is between a one-component number and a two-component number. A fraction is simply a two-component number. And there is no other kind of two-component number. And what does it mean to have two components? It means that two linear numbers are in relation. And that little line actually has a name, but it separates what is called the numerator, which is on top. I know this is elementary, but it's going to be extremely advanced, extremely quickly. So the numerator is on top and the denominator is on the bottom. What the fuck does that mean? It means that the number on top has a non-commutative relationship with the number on the bottom. Do you know what that relationship is? Be honest. Be honest! What if you invert it and the 2 is on top? Is that reducible to 2? Yes and no, because it's a superpositional answer. All the stuff that I'm telling you right now in such cryptic language that you might think that I'm speaking in hieroglyphics or perhaps some loopy tune language. No, no, no. No, you have to listen extremely carefully, and you're going to have to hear this several times before you get it. This baffled every single mathematician who's approached this concept of curvature and eccentricity and evolution. What you're looking at is a continuous plane where every single line is a curve, and the straight line is not straight because there's no such thing. Can I get away with saying that? That's what we're going to end up proving. But what I want to do in this geometric presentation is to show you before I explain it. So you'll actually see it without quite understanding it unless you're a genius. It's possible that you are. And this would be the test if you're a genius or not. I definitely am. That's not a compliment, by the way. It is not proper to call anybody a genius, nor is it proper to call somebody a polymath. There is only one term to describe every single scientist and every single mathematician of any age, of any period of time, however many degrees you have. Your title, there's only one title for a 10-year-old or an 80-year-old with a PhD and a Nobel Prize. You are equivalent. You are what is called a beginner. And that's all you'll ever be. And that's the max, is a beginner. Every other title is shit. Everybody is a beginner until you understand the entire universe. That's going to take you a long time, darling. So what we're looking at here is a chance to actually evolve in the, it's not quite biological, it's mental. Also goes to the British definition of mental. You will go nuts. If you want to understand the structure of the universe, you're going to lose your mind. And I know, because I lost mine. You will too, or you're not going to get this. And that's all the time we have for right now. But I am going to summarize this. Don't worry, I'm not trying to tease you. I want you to notice that the straight line in this evolute sequence, where actually the straight line gets progressively curved until it turns into a circle. And that's what Kepler did. And that's what Sir Isaac Newton did. That's what Bošković did. That's what Poncelet did. And there is a list of 24 other names, all of which are immortal names. They all tried this. And most of them tried it because Newton did. But Newton tried it because Kepler did. And Kepler is actually the genius behind this, except he didn't quite get it. The man who got it best was Roger Bošković, my teacher. And don't you dare make fun of the fact that my teacher is dead. I told you, it'll drive you mad. So what you're looking at is the progressive evolute. That means a transformation. But it's a specific kind of transformation. The straight line, which we're just going to say is straight, because it certainly looks straight to me. Does it look straight to you? Remember, if you take a circle and you dial it so that it's edge on, it's a straight line. Did you know that? Can you do that with a sphere? No, it's already done for you. What does a sphere look like to you? You can't see a sphere, baby cakes. You see a circle. You're seeing a sphere edge on, and all you can see is a circle. That's been proved physiologically. So how do you know that the moon is a sphere? You don't, and there's no way to tell. You see a circle, and that's all you see. You cannot see a sphere. You can't see a spherical surface. You can't see a curved spatial surface. You can't. Unless, really this is a special case of the perfect closed line, which is the transformation of this perfectly open line. That's the nature of the proof that led to my series of discoveries. That this open line, this is the Euclidean line which is made of points. And points only exist on a straight line. That's been proved. In other words, Euclid got that right. But that's where you get quantization from. No other line except the straight line can be quantized. Everything else in the whole universe is non-quantizable. Spatially. I'll show you how this... Jesus Christ. Nothing in the universe is a one-component number. Distance is an illusion. Einstein proved that, and I just told you how you can know that. So there's no such thing as the linear number system. It simply doesn't exist. There's no such thing as distance, because that only occurs on a straight line. And there's no such thing as a point. That means that there's no such thing as a quantum. And so Albert Einstein, even though he got a Nobel Prize for discovering the quantization of light, he's wrong. He actually got it wrong. And Max Planck was correct to hate his own discovery of the quantum. He did not discover the quantum. There's no such thing. So that'll be in the next video, and I am starving. So I'm sorry, but I'm going to have to interrupt this because I don't care about you. I only care about me. So if you want to come back and listen to some more, you're perfectly welcome. But you'll end up just as mad. you'll well, I hope you do tune in again, because madness loves company. I do care about you. It's just I can't see you. So, you know, when you love somebody but you can't stand to be around them, like maybe your sister, how can you say you love somebody if you really can't stand to be around them? Well, that's what it's like to be mad. All right, stay tuned. Thank you very much. I'm sorry. I am so hungry. We'll be right back. Thank you.